Okay, it looks like most everybody who has tried to log on has gotten on, so we'll go ahead and get going. Again, my name is Jody Schollard. I want to thank you very much for attending today's webinar on magnesium die casting, solutions for today's markets. I'm going to be your co-host today. We'll introduce our other host here in just a second. A few housekeeping items to cover before we get going. All the attendees who are listening in, your phones are muted. So don't try to shout at the phone if you want a question answered. We'll talk about how to do that in a second, but just to hide all the background noise, we have everybody's phone muted. Next, this is the latest in a series of webinars that we've done over the last couple of years. Other topics have ranged from kind of introductory to die casting. We've talked about surface treatments for die casting. We've talked about the miniature die casting process. And all of those past webinars were recorded and are located on our website. So there'll be some information going out to everybody following the webinar that talks about how to log in and view those past webinars if you'd like to. Lastly, I want to make a note that we have just recently finished a major overhaul to our website. So if you haven't gone to the Chicago Weight Metal website in a while or ever, I would definitely invite you to do that. It's a fantastic update that we've done. A lot of new content is there, a little easier navigation, easier to search for items. So please, if you get a chance, please go to the website and take a look at what's new. Again, I am Jody Schollard, that's me on the left there, and today I'm really happy to have join me is John Miller. John, appreciate you working with me on this presentation today.
Thrilled to be here, Jody. It's metal I love to talk about. Thank you for
including me. Great. We're really excited about this presentation today. John is our Vice President of Sales and Marketing for Chicago Weight Metal and has an enormous amount of background in magnesium die casting specifically, not only with his 5 years at Chicago Weight Metal, but in other positions with other die casting companies. So this is a great topic. We're really excited to cover it for everybody. Also on the line, not verbally, but at least if you ask questions, you may see their names. A few other experts that we have in-house, Max Gondak, Rob Malarkey, our engineering project managers, and Mike Dimitrov, our inside sales managers. They will be answering questions via the question box that will show how to do that here in just a second. So you will see hopefully a response from them if you get to ask a question. Here is how you do that. In the bottom of your interactive box for the webinar, you'll see a box that says questions. So just type in your question in the box there, hit send, and we will get back to you. Sometimes there's a delay. If there's a number of questions come in at one time, we have to sift through there and make sure we get everybody's question as it comes in. So there might be a little bit of a delay getting your question answered, but please send them in and we'll get to them. If for some reason we miss it or you don't get the answer you want or you want some clarification, feel free to contact us after the webinar, and we'll give you our contact information here at the end, and we'll make sure we get your question answered. So here's the agenda for today's webinar. So we'll talk about what is magnesium. We'll look at where does it come from, how is it processed. We'll talk about there's some misconceptions in some people's minds about magnesium. Hopefully the information we'll provide will help dispel those. We'll look at a bunch of applications and case studies of magnesium, what certain industries are using it for. Hopefully that'll bring up some things in your mind and maybe where you could use it in your particular industry. We'll look at the benefits of magnesium from an alloy standpoint, types of finishes that can be applied, that type of thing. We'll look at a few prototyping options that are out there for magnesium, and then again at the end we'll talk about a bunch of case studies, which is kind of the fun part of going through this to see what other industries are doing. So what is magnesium and where does it come from? This is just a quick, obviously this is a periodic table. Please nobody panic. There won't be a test on any aspect of this if you remember this from chemistry class. We just want to kind of highlight where it is located and maybe a couple of points. Atomic number of 12. It is an alkaline metal, so it's in the alkaline metal section of the periodic table. And just one thing to note, just note its relative proximity to sodium there, right next to it. That actually comes into play a little bit as we get to another couple of topics later in the presentation. So it is what we call a top 10 element. It's actually the 8th most common element on the Earth, and in the top 6 most abundant metal. So it's very abundant. It is located within minerals, so you have to be extracted and refined to actually get the magnesium element out of it. And it's the 3rd most commonly used structural metal behind, as you can imagine, iron and aluminum. So it is very commonly in the structural industry. So we'll talk about some of where that can be used. And it's also 100% recyclable. So that's obviously important these days, and I just want to point that out.
Jody, to talk a little bit more about mag sources. A lot of the material comes from salt water. There's a heavy concentration of mag salts in salt water, and that could be oceans, such as the Gulf of Mexico. Dow Chemical had a facility in Freeport, Texas, that for many years extracted the metal out of the salt of the ocean. Dead Sea in Israel, there's a company called Dead Sea Magnesium, and they're using the salt from that sea or ocean to extract. It also is being done out of the Great Salt Lake, out in Salt Lake City, Utah, by the company Magcorp. And then it's extracted from various forms of rock, carnallite, dolomite, magnesite. These are magnesium-containing rocks that are used in various processes. Basically, there's 2 different processes to extract the magnesium metal from these other materials. After extracting it from salt water, it's usually then sprayed in a drying mechanism, and from that you get magnesium chloride, and then you go through a electrolytic process to extract the metal. The other process is used more for the dolomite, magnesite, and that's a silicothermic reduction of that material, where you basically mix dolomite and ferrosilicon and you burn that material, and under the heat, the magnesium vapor then is collected and reduced, and that's how you end up with the metal. So it's extremely plentiful, but it does need to be extracted, and it's done in various ways.
And then following up to that, you look at once the magnesium is actually refined, and then it's put into an alloy form that you can use for the various processes. In this case, we're focusing on the high-pressure die casting process, so we'll look at one of the alloys that are most commonly used, and just give you a little bit of a quick explanation of how the nomenclature works for the alloy. So this is like I said, one of the most common designations, which is AZ91B. How the name comes about is the first character A is the highest alloy content in the alloy. So A being aluminum, so that's the highest percentage of this alloy is aluminum, or the alloying element is aluminum. The next character is Z for zinc. That's the next highest. And then 9 and 1 are the relative percentages of those two. So in AZ91B, it has 9% aluminum, 1% zinc. So that's how the designation comes about. And then very small percentages of other compounds, and then the bulk of what's in there is magnesium. The D refers to the revision level that alloy is at, and then the F is the temper designation, which is not typically specified when we see drawings or that type of things come in. So if this is the alloy that you want to designate on your drawing, putting magnesium AZ91B is perfectly fine. Everybody understands what that means. Some of the available processes for magnesium that are available. It comes in sheet form, so you can do stampings and other types of things that you can get out of a sheet format. It comes in extrusions and billet form, so you can machine it. It's a slightly different alloy designation for the billet, but it's very similar in material properties. It also comes in various types of gravity cast formats. where you can contain cast it, investment cast it, plaster cast it, that type of thing. And then, as I mentioned, what we'll focus on is the alloy that is available for high-pressure die casting.
Okay, this next this slide here is really just a performance comparison. And to keep it simple, I just wanted to make sure you understand that the numbers that you see are really just the ranking or the ordering of how properties would be compared. And we're looking at aluminum 380, magnesium AZ91D, and zinc number 3, which are the three main alloys for each of these families of metals. For those of you that want to see much more detail, we can certainly follow up with detailed physical and material properties. What I wanted to point out, though, is looking at that middle column of magnesium, where the number ones are. Where does magnesium outperform both aluminum and zinc? And strength to weight ratio and density are far and away the most important of those things in terms of where magnesium greatly exceeds the other metals. Energy absorption is also rated number 1, and so is machinability, though admittedly machinability, it's not such a, we're not looking at magnesium as being that much greater than the others, but it does take less power to machine magnesium than other metals. Other than that, you see a lot of number 2. So for the other properties, magnesium falls well within the normal parameters for other types of structural metals. Maybe die life, though, it's important to note that die life is number 2, but it's true that it's much, much better than aluminum and not quite as good as zinc. So certainly, other than zinc, die life is very, very good for magnesium. And the only 3 that you see there is for thermal conductivity, and my experience is that it's also not such that it's a great distance from the other 2. In fact, as we talk more in this presentation, we'll talk about several applications where magnesium is very effectively used as a thermal heat sink. So even though properties are not quite as good for that as zinc or aluminum, it doesn't preclude it from being used in those kind of applications.
And with the next few slides, we're going to talk about some of the economic and production advantages of magnesium die casting, or of magnesium in the die casting industry. And this slide is going to go back a little bit to what John just mentioned about die life. Obviously, one of the factors for a die casting application is the number of pieces you can get out of a die cast die before it needs to be replaced or some significant refurbishment to it. So what we tried to do on this slide was to show a comparison between an aluminum die for an aluminum die cast part versus a magnesium die cast part. So on the column on the right, if we assume, as it shows on the top, assuming a tool cost of about $75,000, which is maybe on the high side of a lot of die cast applications, but we just use it for reference. And the column on the right showing the average tool shots that you can get out of an aluminum tool made for aluminum die casting, where you get about 100,000 average shots before some significant replacement or refurbishment needs to be done. So if you amortize the $75,000 tool price over 100,000 shots, obviously that's a 75 cents per part cost over the life of that tool. For magnesium, we see about 3 to 4 times, probably closer to the 4 times the die life. So for the magnesium die, you're going to get about 400,000 shots. So when you look at that over the 75,000, it drops the per part cost down to about 19 cents. So this is one factor where you can see some advantage of looking at magnesium versus aluminum and what the part price savings would be over the life of that tool. In this case, would be about a 56 cent savings over the life of that tool. The next factor to look at for any kind of economic standpoint is material costs, and the next couple of slides deal with that. So when you look at magnesium versus aluminum or zinc, obviously the density is much, much different for each. So it's just interesting to show, if you look at the densities of each. Magnesium is 0.066 pounds per cubic inch. Aluminum is about 50% higher than that, and then zinc is much higher, about 2.24 pounds per cubic inch. So out of 1 pound of mag, you can get about 3 parts. 1 pound of aluminum, you get 2 parts, and 1 pound of zinc, you can get under 1 part, so about 0.8 parts. And this comes in a little clearer here in the next slide. But density is the other big factor into how the economics play out. So look at this slide a little bit, and this is showing kind of a different way to represent how the density plays into material costs. And this is a snapshot of where material costs are right about now. So magnesium is about $1.95 per pound, zinc is about $1.18 per pound, and aluminum is about $1.08 per pound. So that's just on the material cost itself. And when you look at that in a cost per cubic inch, so you take the density into account, you can see that magnesium and aluminum come pretty close together, even though the actual cost per pound of the alloy is much different. When you break it down and include the densities, those two come pretty close together. And then when you look at factoring in some other factors, say, and which John will talk about here in a little bit, magnesium, we're able to design parts that may need about 20% less wall thickness than aluminum. So if that's the case for your part, then again, that will help reduce the amount of metal content and bring down the price the cost that much further for the actual alloy content. Another factor is that magnesium, the cycle time that you can achieve on magnesium die casting is slightly better than aluminum. So again, when you look at it from a total project standpoint, all these factors go into to helping magnesium offset, I guess you will, the cost per pound difference that you see on the screen. When you factor in everything, it actually comes in very, very close, maybe even sometimes better than aluminum or zinc for an overall project standpoint. And one of the things I was doing while we were going through this, I was monitoring some people's questions as they come in. So there was a few people that had a question about kind of the stability of magnesium prices over the last 4, 5, 6 years. They have heard things that pricing may be very volatile and that type of thing. So I wanted to take a minute here and point that out. It looks like Dan, Tom, and Frank had all about the same question about the stability of the material price. Actually, magnesium over the last 5, 6 years has been very, very stable. In fact, maybe more stable than aluminum. So it is, pricing standpoint, it is very stable, and we see nothing in the market that says it's going to be different. So just wanted to point that out as we go along here.
So talking a little bit about mechanical properties and other performance aspects, and we're going to first talk about corrosion. This has to do with maybe some of the myths that are out there about magnesium. But we and many other die casters, all the die casters nowadays are using the latest version of the ASTM designate for the alloys. And so for us, that's AZ91D, the D being the latest revision. And that revision has really solved issues with atmospheric corrosion. Back early days of die casting, yes, magnesium hadn't been refined enough to where they understood what was happening, but with very low percentages of iron and nickel and copper in the alloys that we use now, AZ91D is actually outperforming aluminum and certainly outperforming carbon steel. What you see on the chart is showing you the mils, or thousandths of an inch, that you would lose per year. MPY stands for mils per year. So magnesium 4, aluminum 13, carbon steel 30. This is according to testing that's been done under ASTM B117 with a salt spray and fog test. So the high purity alloys, the D version that we're using of the alloy, is no longer an atmospheric corrosion risk. Now, some of you may have heard that there's an issue with galvanic corrosion. Galvanic corrosion can occur with a number of different materials, magnesium being one. And yes, magnesium is more likely to have a galvanic corrosion issue than the other metals, but that's more of a design issue, and Chicago white metal or other die casters can help you design around that so that that's not an issue. This chart shows weights at equal stiffness, and I chose this chart because really when you're designing a part, you're normally looking for a part to hold its shape under some kind of a load, and so stiffness is sometimes much more the area that you're looking at more so than ultimate strength. So looking at stiffness, you can see mag outperforms aluminum and steel by a pretty good margin. But this is showing weights at equal stiffness, or another way of saying it is mag allows for lighter parts at equal stiffness. You could turn it around and you could say at equal weight, the mag parts could be much stiffer. The point being that combining the stiffness properties of the alloy and the density, it really allows you to achieve what you need from a design and still capitalize on the low density and save weight in your application. And another benefit of magnesium is really shown more and more now with some of the latest electronics. So there's Steve Jobs there, using him as an example. Today's society, with the push towards lighter and more complex handheld portable electronics, has really been a bonus to magnesium, because magnesium provides that lightweight and the stiffness so that when you package a part like what Steve is holding, you don't have to worry about the part being crushed and affecting the internal components. So it's got the strength and stiffness that would be better than plastic. It's got that, more of a feel of quality presents itself compared to plastic as a higher end material. It allows then the use of magnesium allows sort of to get away from some of the materials that might be considered more old school, such as steel or zinc and aluminum. So magnesium is really helping to propel sort of more of a marketing capability that is more, not, I don't want to say exotic metal because that would sound like it's high priced, which it is not, but it is a very well engineered material that allows for well engineered part designs. And we'll talk a little bit about some case studies now. First of all, this in kind of an overview, and then later as we get in the presentation, we'll go in depth on a few selected products. But magnesium is used in a wide variety of applications. So one of those we're combining medical and dental applications. Chicago white metal has a number of products that fit this type of industry and application. What you see pictured, for example, in the black, a two-piece wheel for a wheelchair. And what's interesting about that is if you can see the little gear teeth, those are all as cast. The two pieces were held together with 4 fasteners, but all the diameters, including the bearing diameter and so on, were all as cast. No machining required with that magnesium design. The bottom left is a multi-piece portable medical electronic device. And we're going to go much more in depth with that. But portability, due to its low density and very thin wall applications, housing electronics where you need stiffness, it's an ideal place to use magnesium die casting. So is the part that's more in the center and down to the bottom. If you picture yourself sitting back right now in the dentist chair, you might be looking up at something very similar to that. That's a dentist light. And lighting now is changing throughout all kinds of industries. So even in dentistry, they're going to LED lighting. And so this is a new housing for that light that was designed, and part of the structural support for it also, all done in magnesium. And if you think about that low density of magnesium on a cantilever beam, like on the end of the arm for a dental light, again, an ideal choice for magnesium. It's got low inertia and mass. It allows the dentist to easily reposition it, and at the same time, it's not going to drop or move once it's in the right position. So it allows for the whole structure to be sleeker, and ultimately giving better performance in a cleaner design. Other products on the top right is showing a medical printer. The pieces on the left and the right are like the wings of it, the side wings, and they're shown open, but those would all be closed in an actual unit. But it's a case where mag was chosen over plastic or sheet metal due to its stiffness, ability to hold close tolerances, and be able to design in many, many features that would be hard to do in sheet metal. The conglomerate of little parts that you see below that are a number of pieces that go into a portable oxygen compressor or a pump. It's a wearable device, and so that's why, again, you'd want the low density of magnesium. It also is exposed to a little bit of moisture that's in that air, and all these components then are able to withstand that because, again, mag's corrosion properties are actually pretty good. The next slide talks about electronic applications, a very broad category indeed. I'll just touch base on some of the ones pictured. One is maybe hard to see, but the top left is a large heat sink. That is about 18 inches long, 6 inches high. It replaced a part that they had tried both in zinc and aluminum. And as I mentioned earlier, I've seen many cases where magnesium performs very, very well as a heat sink. In this design, what they were able to do in magnesium compared to aluminum was add more fins and have the fins thinner. And so therefore, you essentially got better cooling than you did in aluminum. And the reason why it's selected over zinc is because it happened to sit up on top of a rack-mounted device, and the zinc part, being 4 times heavier, was more of a top-heavy design and a little bit more of a safety concern about this rack having so much weight up on top. So it was a perfect example where magnesium's ability to dissipate heat was very adequate in allowing for the other benefits of magnesium. Ultimately ended up with a better design in magnesium. There's a multi-piece camera that we show pictured, a Sony camera we'll talk more about later. The two middle parts, sort of an orange color and a yellow color, there are 2 different versions of GPS technology, so again, electronic housings that are used for surveying, for example, where you'd want to have portability in a lightweight electronic housing. The lower right-hand corner is a digital projector. That projector contains maybe 10 or 12 different magnesium products. This is a high-end digital roadshow or concert event type of projector. So even though you may not think of a projector as being portable, when it comes time to set up a show, having to load and unload and set all these things up and transporting them across the country, across the world, flying them places and so on, the weight matters. And so for that reason, magnesium was a good fit for that application. The next slide covers different types of products in the sports and recreational industry. And again, wide variety, just some shown. The red colored part is a mountain bike suspension or front steering fork part, and those tubes are hollow because inside them goes the springs or the oil and damper mechanisms to provide the shocks that are put on mountain bikes. And magnesium allowed those long 12-inch or so tubes to be cast with hollow diameters inside that did not have to be machined, even though they're pressing in bearings and so on. Tightly toleranced, very little draft. I think it's something like half a degree draft inside those tubes. And obviously some of the other products would benefit from lightweight magnesium, like an archery bow, or what's pictured there is a fishing reel, or a high-end spotting scope that was originally designed to be used for hunters and ends up being well received in the military as well, where you're certainly appreciating the lighter weight, having to carry around all the equipment. And other portable devices such as a scooter or tennis rackets, sunglasses, and on and on and on. There's a wide variety of applications in this industry. Next slide is, we'll call it power tool applications. It's a number of lawn and garden products, but not necessarily all lawn and garden, so we call them power tool, but it's another area that magnesium is used quite a bit. There's a family of parts pictured there. They're in a pneumatic nailer. The cylinder sleeve that is used to compress the air is a one-piece casting, and the ID of that, maybe 9 inches long, is as cast. And so it's very thin wall, very little draft. and allows a lot of cost to come out over what it would be if you had to do it in aluminum where things would be machined. The lower left hand is a skill saw, and this particular company had in-house capability of doing aluminum casting, and so they still sell many that are made with aluminum, but they were able to lighten it with magnesium and then offer it to contractors and professionals at, of course, a higher price point. So that's another thing you can do with magnesium is sometimes just market its benefits and enable to have a higher price point. Lawn and garden products such as crankcases for the string trimmers is a very common use, and again, typically as cast, no machining, even though bearing bores are pressed in and so on. Oftentimes these products have consumer grade, where you might use a plastic or aluminum part, and then professional grade or contractor grade where they would go with magnesium. The next slide is automotive applications, and far away this is the greatest use in terms of total number of pounds of magnesium due to the size of the parts as well as obviously the volume. And there's many, many parts. Not going to try to list them all. I try to group some of them into categories: interior, chassis, powertrain. Some are pictured there. You may not know, for example, that almost all steering wheels now are magnesium. Typically cast out of a different material, different alloy called AM series alloys, either AM60 or AM50 that has very high ductility and absorbs crash energy. And the same would be true for instrument panel support beams. There's about a third of a beam pictured on the lower right that would support an instrument column. It would support the brake pedals and so on, but it would also span some of the dash. But there are a number of applications where the full cross-car beam is made out of magnesium. And again, this would be used in one of the series of alloys that would be very high ductility and absorbing crash energy. The chassis parts, listing their front and rear modules, grill opening reinforcements, these are maybe a little bit harder to picture and describe what they are because as a user of an automobile, you may not see these, but this is sort of the new area, up-and-coming area of large products that are eliminating multi-piece weldments or fabrications and doing it as a one-piece in magnesium and saving considerable weight and helping handle crash energy and help for vehicle dynamics and performance. And of course, the number one reason why automotive applications are using so much magnesium is because of fuel economy. And finally, other applications. Jody mentioned when he was talking about the periodic chart that magnesium is in the alkaline section, and so it handles the alkaline of concrete very well. So there's a number of concrete tools that are done in magnesium, but all kinds of other products too. A hand cart, a luggage cart, that would make sense. Again, have the lightweight magnesium, a nice stiff L-shaped bracket at the bottom that gives you the low weight and excellent physical properties.
Okay, so if we talk about a little bit about what type of prototyping options are available, pretty much this is the same options that are available for the other die-cast alloys, aluminum or zinc. And a lot of it depends when a customer asks us what type of prototyping suggestions we have. A lot of times it depends on what you're going to do with the parts, how many parts you want, what type of testing is going to be done, that type of thing. But magnesium can be machined from billet. The AZ31B is the alloy that's out there that comes in billet form. Can be machined just like a 6061 aluminum would be, so it can be very easily machined from billet. We can also do a rubber plaster mold process. There are a couple of companies out there that we suggest people work with. And this is great for when you need maybe between, say, 10 and a couple hundred parts. If you're going to do some testing or a large number of qualification builds, that type of thing, that's a great process for that because you get fairly low tool price, and the pattern that they use can be used over and over again, up to say a couple hundred pieces before they have to make another one. So that's a great option. And then for some larger parts, maybe sand casting is a better option for prototyping. So there are a few out there, And again, this is you'll have about the same choices in magnesium as you do for any of the other alloys.
To talk about surface treatment options, basically you can finish magnesium much the way you would with any other die casting, whether it's aluminum or zinc. So whether you need a decorative finish or just some additional wear resistance or corrosion barrier, those all can be done. So electroless nickel would be a way of providing additional EMI shielding if that's required, though obviously magnesium metal provides very good shielding properties as it is. But powder coatings, liquid coatings, e-coatings are all paints that can easily be applied. In addition to that, traditional mechanical finishes such as tumbling, deburring media, blasting. You may use aluminum, zinc, or glass bead blasting with magnesium. So finishing is very similar to what it would be with other die castings. And in fact, there's many applications that don't require any kind of finish at all. A few of them are pictured right here. Because again, magnesium, atmospheric corrosion-wise, not much of an issue. And so depending on the environment, you may not need any coating at all. The one pictured on the left is an internal component to an electronic barcode scanner or printer. Magnesium is selected due to its lightweight and being able to hold this then easily at the end of your hand, end of your arm. The middle part, that is about 16 inches long, and it's an engine accessory bracket. So that mounts to a cast iron engine in an automobile, and then mounted to this are idler pulleys and air conditioning compressors and things like that. This was a conversion from aluminum die casting to magnesium. It helped the automobile company reduce weight, but what was interesting is they were able to do that without any extra cost because some of the machined mounting points in aluminum were able to be cast in magnesium, plus the longer tool life, and as Jody had explained, that's a real benefit. So the net effect was they were able to get the reduced weight without any added cost. And no corrosion issues, even though it's mounted directly to a cast iron engine. There may be an aluminum washer, but otherwise, even though it's exposed to road salt and splash, not an issue. The one on the right is used in hundreds of thousands of vehicles across the world. Chicago White Metal is exporting this daily. And it's an LED heat sink and LED circuit board cover. And it also serves then as a heat sink. It's made in magnesium because it can be done then without any machining, fairly thin wall, provides the stiffness so that everything seals nicely, because you can't have any water that would penetrate this and harm the electronics inside. We do 100% leak testing, and the leaks that we get as cast are extremely low.
And John, before we leave this section, I was looking through the questions, and there's a couple of people asking about how does magnesium hold up in like marine environments. And I think this is probably a good place to answer that. Magnesium, when it gets around salt, and this is going to go back to our salt sodium atmosphere, this goes back to the periodic table and it being so close to sodium, it really starts to degrade faster in that type of environment than it would in another environment. Not that you can't do it, but you do have to look at some specialized coatings, some marine grade coatings that you can apply to magnesium die casting to have it survive the life. And so maybe some additional testing needs to be done to make sure that the coating that's being applied is suitable, but I just wanted to point that out here since we had a couple of questions come up. And so now we'll start to look at a few specific case studies. John mentioned a few of these briefly as he was going through the overview of magnesium applications. This is a large shoulder-mounted camera system for Sony. And as you can imagine, lightweight is important. There are electronics inside, so EMI shielding is important to protect the internal electronics. This part has 11 different die castings associated with it. Some of the internal parts, the large internal structural parts that you see are aluminum, but all of the majority of the outside components are all magnesium, and so that adds to stiffness of the unit, the durability of it in case it gets dropped, that type of thing, but also the lightweight aspect of it. 5 of the parts that are in here were cast to net shape, and that's exactly how they were used, no machining, that type of thing. Other parts get some amount of machining, either some drilling and tapping, that type of thing. And then all parts get some sort of coating. The exterior parts get powder coated for the cosmetic appearance. But this is a great case study to show that the quantity of parts that can be used in this application and the reason for its use.
Jody, this is a part that was briefly mentioned. I'll go into just a little bit more detail now. This is one of many award-winning applications that Chicago White Metal has made. And basically, I want to point out that compared to plastic, magnesium won out because in the end, the walls could be thinner and still provide the stiffness necessary. So ultimately, the part can be done more compact and for less weight than would have been in plastic. So the total weight of a multi-piece like this was 1.7 pounds. There's all kinds of holes, as you see noted there, that are cast-to-size. Coatings involve conversion coatings, and then 1- and 2-color powder coating with silk screening, pad printing, and so on. But it's, again, a wonderful example of a portable electronic device that is extremely well done with magnesium.
And then the next case study we'll look at is, again, we saw the image of this previously. This is a part that's used in a GPS, it's used in a GPS setting for construction equipment. So it actually is mounted to the pieces of equipment that lay precision asphalt and concrete surfaces for roads, maybe airports. And so this unit actually helps control the actual equipment up and down as far as how much asphalt to lay in certain areas. So it's a very, very precision piece of equipment. It has to be very durable. If it falls or gets knocked around, it has to be very durable. It has to be environmentally protected from water and dust and that type of environment. Again, lightweight was important. The EMI shielding for the electronics was very important. And then there's this part has a pretty good amount of critical CNC features that are machined, and then gets a conversion coat followed by a powder coat, and then pad printed some graphics on it. So a lot of value-added items that we put onto this application. And it's a great example. And then next is the scope that John mentioned earlier. This part was originally developed more for commercial uses, bird watching or any type of other personal scope use. But because of the durability and the precision with it, it's actually the military started seeing the benefits of it. So that's where this part has mostly gone into. Very, very rugged, 100% waterproof for all conditions. Some of the features in this unit get some extremely tight machining done to it. So it's a very, as you can imagine, very critical features for alignment and that type of thing. Very, very small. The whole weight is 8 ounces. And some of the wall sections that are in this magnesium part go down to 39,000. So very, very thin walled with some sections, and another great example of where people are using magnesium.
This particular part is part of the projector case that I described earlier, where you would take it on the road. And another application that I didn't tell you is that they also put some of these magnesium parts in a larger version of that projector that is not really designed so much to be portable, but it does extremely high-end projection. So when you were watching the Olympics in Sochi or in London or in Beijing, many of the opening and closing ceremonies were done by use of projecting down onto the floor of the arena and using these high-end projectors. So there's a number of parts that are inside this with magnesium. It needed to be stiff and strong and very dimensionally accurate, and they couldn't achieve that with bending sheet metal or with plastic. it also serves as helping to dissipate the heat that's given off by the high-intensity lamp. So this is an award-winning part, one of a string of award-winning parts. 2013, both NADCA and IMA award winner. The main reason why it was an award winner is that this is an example of, again, cost savings and efficient use of magnesium. What you see down in the lower part pictured is the before. The before were 2 parts. And then Chicago White Metal Engineering worked with the customer to come up with a design that would allow for a 1-piece design. And with that, the customer was able to realize a 40% savings and greater stiffness, greater accuracy, less logistics issues, less inventory to hold, and so on. So many, many benefits. The automotive mirror shown here is another part that is won awards, and this is an example of a part that could be done and is done in zinc and aluminum as well. But for high-end automobile companies looking to make the performance of their car better than their competitors, they're turning more and more to magnesium. And so even though this particular part, which is the mirror mount, is only saving a small amount, it's part of the overall strategy to reduce weight and improve performance. The part itself is fairly complex. Even though it's small, that particular ball end is held to what really is essentially machining type dimensions, but it's held as cast. And in order to cast that round or spherical shape, you've got to use 2 halves of the die. So holding that shape as cast is quite a challenge, but it is an example of what can be done.
Okay, well that's going to conclude the majority of the content for today. Just additional information regarding the webinars. We mentioned this on the last one, but we're still doing it again. If you attend 3 of the Chicago White Metal webinars, you can get a 5% discount on your next tool order with us. So we're keeping track of who attends, and the next one should be out in a few months, the next webinar. So please make sure you sign up and attend the next one, and we'll keep track of how many you've attended. We've got some handouts that will be emailed to the people who registered for this webinar, some technical papers that reference some of the myths with magnesium, and hopefully the information provided today helps dispel some of those. The alloy of physical and material properties that John highlighted a little bit earlier, we can send out some detailed tables for that. And also the link to this webinar. We're recording this, and if you want to go back or have some other coworkers go back and take a listen, we'll give you the link for that. Lastly, just want to make sure again to invite you to visit the Chicago White Metal website, and specifically the Design Center. Has an enormous amount of information contained, past webinars, alloy selection information, that type of thing. So please, I invite you to go through those. And lastly, here's our contact information. John, definitely want to thank you again for helping with this presentation. It was, I think, very beneficial. So if anybody has any questions that you weren't able to ask during the webinar, feel free to contact John or myself, and we will do our best to get back to you. So, John, with that, I guess that's going to be it. If you have anything else.
I don't, Jody, but I certainly appreciate you allowing me to participate today. And yes, I see there are questions still continuing to come in. Our panelists are working on responding to those. Feel free to continue to ask them, even though we may be closing the presentation part of it. We'll continue to ask or answer your questions as they come in.
That's right. Yeah, we'll keep that open, and so keep the questions coming. But if you can't answer them, can't ask them today, feel free to take down our information and contact us at any time. So thank you everybody for attending, and hope you have a nice rest of your day.